All right, so here's another kind of category of thing that can happen. This is already a matrix equation, right? So they're asking me to verify that the matrix y prime is equal to a times the matrix y, and they've given me y and a, and this is I swear to God as easy as it looks like it should be, in exactly the same kind of vein that we've been doing. You need to calculate y prime. And so you go, it's 6e to the 6t and minus 2e to the minus 2t and 6e to the 6t and plus 2e to the minus 2t. So that's y prime. And then on the other hand, I need to calculate a times y. And the only thing that's hard here is that you have to make sure that you get a times y in the right order. Why would... Exactly. Well, yeah, it is not particularly hard, but it bears noting that you cannot reverse matrix multiplication. Yes, matrix multiplication and function composition are the kind of two go-to non-commutative operations that you know. Also, the other one that I like to use as an example is that opening your garage door and driving your car out of the garage are also not commutative operations. Right? If you I mean, I'm not clear that it's not. I'm not claiming that it's not possible. I'm claiming that they don't give the same result. One of these things you can go to work, and the other one you spend the day talking to the insurance company. Yeah. Well, I mean, in the current world situation, I'm sure the only question they would ask you is, why are you leaving your house? Not, why are you drunk? Yeah, it's really flipped expectations lately. All right, so to do this multiplication, we need to know how to multiply matrices, which I think is why I'm like, that's kind of what I'm trying to highlight here. So if I have a matrix that's made out of rows this way, times a matrix that I think about as being vertical columns, then the resulting matrix that I get is row 1 dotted with column 1 and row 1 dotted with column 2 and row 2 dotted with column 1 and row 2 dotted with column 2. I don't really care how you think about this, but that's a method to get the right answer. Otherwise, you can kind of think about picking up the columns and dropping them on. That works fine as long as you kind of go in the right order. Oh, did I do this backwards? No. Okay. So, out of this thing, I should get a first entry that's row 1 dotted with column 1. So that should be 2e to the 6t plus 4e to the 6t. And then I need 4e to the 6t plus 2e to the 6t. All right, so I did the column 1 things first. And then I need a 2e to the minus 2t minus 4e to the minus 2t. And a 4e to the minus 2t minus 2e to the minus 2t. You guys with me on that? Okay, and that should give me a 6e to the 6t, a minus 2e to the minus 2t, a 6e to the 6t, and a 2e to the minus 2t. And again, I'm kind of checking. This was the right-hand side was equal to this, right? Addition on that bottom part. Can you... No worries. You had me real paranoid there for a second. Because I was like, see, it worked perfectly. All right, so now I'm verifying that the left-hand side that I got from differentiation is the right-hand side that I got from multiplication. And it looks like it is. So I think I am good to go. Check. I have verified that this matrix solves this matrix equation. How is this different than the vector thing I was just doing? Say that again. Yeah, it's a little bit less gross for one thing, which is kind of nice. You might notice that this matrix Y here, if I compare this to problem number 1, this is the same coefficient matrix that I had in problem number 1. And in problem number 1, I had Y was AY. And they told me that lowercase y, right, the vector solution, was C1 times 1 e to the 6t plus C2 times the vector 1 minus 1 e to the minus 2t. And you might notice that the pieces that I have basically correspond. This stuff, 1 by e to the 6t, is this first column here. And the second column is this other part. So what they're kind of doing here is saying, yeah, actually, by the way, you can rephrase this instead of as a vector, you can rephrase it with a matrix. And then your solution is C1 times the first column of the matrix plus C2 times the second column. Does that make sense? Maybe. Maybe not. Have you guys thought about a matrix as a set of column vectors before? Like it's a bunch of vectors put in a box together, right? And one of the special things about matrix multiplication is that a way you can think about matrix multiplication is that it's just the I'm going to scoot down below this thing a little bit. A way you can think about matrix multiplication is if you have a matrix A times another matrix that's made out of a bunch of columns, that you can say that this is A times the first column. Not plus. Plus is dumb. It's a matrix made out of A times the first column and A times the second column and A times the third column. right? And those are the column vectors in the new matrix. So if you're going to multiply the same matrix by a bunch of vectors, one way you can do that is you can just put all the vectors into a matrix, multiply the two matrices, and then the answers for each one are just the columns. That's a trick that sometimes students find really early, and sometimes they happen upon it really late. I didn't know if anybody's highlighted it for you guys, but it is a little bit handy here in that I know this superposition principle is going to hold, and so in order for me to verify a solution, one way for me to do that would be that kind of icky thing that we did with the first couple of problems. And then, if I assume the superposition principle still holds, which it should, then I can just do this thing instead. Does that process sort of make sense? Okay, hearing no complaints, I'm going to assume it makes sense.